disks, and he tries to link those observations to planet formation. So he did his PhD in ETH, quite close from here, and then he moved to Michigan for 2 years, and now he's back in Zurich. So please, Gabriele.
Thank you. Yes. Hi, everyone. Thank you, Saburo. Yeah, my name is Gabriele. I started here about 2 months ago, and I'm really excited because I'm learning a lot about theory that so far has been a field that's a bit missing in my curriculum. So I want to bring you back to 2018 to start this talk. This is the collection of the D-sharp disks imaged by ALMA. And this is really the moment where I started being interested in planet formation. So this gallery shows a bunch of protoplanetary disks imaged by the new ALMA facility, or back then it was newly upgraded. And we saw something that we were not really expecting. We saw all these beautiful disks showing all of the type of structures we can imagine, right? The contrast is not great in this room, but you see we have a lot of rings, we have gaps, we have some spirals up there. There is another one here, for example. And all this diversity in the structures begs the question, where does this come from, right? And of course, there are several explanations, and one, or maybe the most exciting one, is that several of these structures are created by forming planets that are interacting with the disk material. If we simulate this scenario, we see that, so here you have a protoplanetary disk simulated with a protoplanet, a gas giant that is forming in the disk. And if you let the simulation run, you see that both in the gas and in the dust, we create some of these structures that we observe. We see spirals, we see some gaps and rings. And so it is possible indeed that these structures and these shapes are created by planets. So we digged a bit deeper, and we looked not only at the dust, as I was showing before, but we also looked at the gas and the chemistry. This gallery shows the same disk seen in different molecules. We have some huge molecules, or not huge molecules, but molecules that are present throughout the entire disk. For example, CO, it's very bright. We have 13 CO here. We have CN, which apparently has a ring in the outer region of the disk. And then we have a bunch of molecules that are only visible in the very core of the disk, where the temperatures are a bit higher. But what is most interesting to me in terms of gas is that with ALMA, we can really measure the velocity of the gas to an extremely high precision. And this allows us to explore the environment of these forming protoplanets. So if you have a planet forming in a disk, you can imagine that the gravitational interaction between the planet and the disk material perturbs the surrounding gas, which moves then at a different velocity. So the central plot here shows the deviation in percentage between the actual motion of the gas and the Keplerian motion that we would expect if there were no perturber. And you see that close to the planet, we have quite some perturbation. Now we can try to detect this perturbation. If we simulate a disk, this is what we obtain. You can imagine this being the image of all the gas in a disk moving at the same radial velocity. Okay? Now, if the disk is uniform and smooth, you have this type of butterfly shape. But as soon as you insert a planet, because you have those perturbations up there, you create some sort of, we call them kinks. So this inhomogeneity in the along the edge of this butterfly shape. And we can now have a look at our data, and we see that there is clearly the same kink in our data. And we know this is true, or we are convinced this is true, because we observed it in different epochs. We observed it with different molecules, tracing different layers in the disk. And so we really do believe that this is a genuine perturbation of the gas kinematics in the disk due to a planet. Finally, we can look at scatter light images. And here again, we probe something different. Here we probe the surface, the dust at the surface of the disks. And we see again a bunch of spirals. We see some shadows, for example, here, right? We think there is an inner disk that is tilted very close to the star. And this produces the shadows that are then seen in the scatter light in the outer region of the disks. And here again, we try to reconnect all these beautiful structures with planet formation. Now, this is not easy, especially if you want to see these planets. And in high contrast imaging, which is what I really do actually, not all this disk stuff, we have two main issues. The first one is the contrast, and the second one is the resolution. So the comparison we always make is that we are basically looking at a lighthouse, okay, a very bright lighthouse. And next to this lighthouse, there is a firefly. And this is what we have to detect. When we look for planets, we are looking at that firefly close to the lighthouse. And actually, we are doing from one side to the other of the US. This is roughly the scale. So how do we do it? Well, we need big telescopes. We need very precise instruments. And in particular, we use what we call the 3 pillars of high contrast imaging. And by the way, if I say something that for me it's obvious, but it's not, just interrupt me and say it, okay? It's not a problem. So first of all, we have adaptive optics. You can imagine the atmosphere as being a bunch of cells with slightly different density and temperature and properties. And therefore, when the light goes through the atmosphere, it refracts in different ways, and therefore it's never really stable in our instruments. And so to correct for this, we have adaptive optics. Basically, we measure the star every 20 milliseconds, and we have a little mirror that reshapes itself, or we have some actuators that reshape a little mirror and correct for the aberration of the atmosphere. And this is done 50 to 100 times every second. This is how it looks like. So this is a companion. It's a bright companion. This is the PSF of the star at the center, and you see that it's moving a bit, but here we lost the adaptive optics. All of a sudden, we are not correcting for the atmosphere anymore, and then we are correcting again. And you see that this is really essential, because if you don't have this, first of all, your planet will be spread around over many pixels instead of being fixed at the same location, but also the star, of course, is creating more noise everywhere in the image. The second important tool that we use is the coronagraph. You can imagine it as being just a piece of metal. Of course, the technology is a bit more complicated, but it's a piece of metal that covers the star and therefore helps you with the contrast. I think this was the perfect natural example. I was lucky enough last year to look at the eclipse in the US, and we saw Jupiter for a few minutes, right? When the sun is not completely covered, you don't see Jupiter. The sunlight is too strong. But for 4 minutes during the eclipse, we could see Jupiter right next to it, and it's beautiful. The same is with these coronal ejections that were visible during the eclipse. So this is the second tool that we use. And finally, we have post-processing, which helps us gain another factor of 10 to 50, depending on the situation. And here I don't have boring slides, just for your. I didn't want to bore you too much. So let's have a look at some of the successes of direct imaging. The first one is really this iconic system. It's called HRS799. It's one star that is hosting 4 planets, and we see them orbiting. So there is 1 over there and 3 over there. And you see, by the way, if you look, so this animation starts from 2009 and goes to 2020 something, and you see the improvement in our ability to detect these planets, right? At the beginning, we have more noise, and then here, the noise is basically gone, and we can really see them. And you can imagine in the future it will be better and better, especially once the ELT will come online. Let me try to do this. Yeah. Another iconic system, Beta Pictoris. We have 1 planet over there. There is a huge debris disk in this system, imaged with IRS and a bunch of other instruments. And now we know there is even a close-in planet detected with radio velocity, and we also took the spectrum with optical interferometry. And then we can move to space. This is the first spectrum, or the first planet detected by JWST. Bunch of filters in the near infrared, but especially it was super interesting because for the first time we looked at the planet in the mid-infrared at 11 and 15 micron. And this helped us constrain the overall shape of the planet, especially in this area here, where we can really focus on constraining the radius and the temperature of the planet. Especially the radius is always being difficult because in this area, you have a bunch of other parameters you can play with, like the amount of water or the gravity of the planet and so on. And this doesn't really allow you to constrain the radius. And finally, I want to conclude with some disk images. So these are two of the most famous disks that we imaged so far. AB Auriga, beautiful disk. The contrast is really not great here. I'm really sorry. But basically, it's full of spiral structures. We think we see gravitational instability ongoing. So there is a lot going on in this disk. It's a very complicated disk. I'm usually trying to stay out of it. And finally, here we have the iconic system PD70. This is the first system where we are really convinced we are seeing forming planets. This one here is the first forming planet we detected. And then actually here, there is a second one that is not really visible in this image. But this is a cool system. Every time we have a new instrument, we look at it. The MRS detected tons of water, for example, in the inner disk. So there must be a mechanism by which water from the outer region of the disk get transported inwards, crosses the cavity where the two planets are forming, and then gets stuck for a bit in the inner disk where it evaporates, and then we can see it. So it's really a cool system. Okay, this was a little bit my introduction. And now let's have a look at some really cool data, in my opinion. So in the next few minutes or 20 minutes or so, I will discuss our JWST NIRCam search for young protoplanets, the first measurement of extinction from a protoplanetary disk and why I believe this is really a crucial measurement. And then we conclude with some discussions on circumplanetary disks. So for those of you not familiar with this, JWST was launched on Christmas Day in 2021. And since then, there have been maybe 7-8 months of calibration and commissioning, and we basically make sure that we understand what's going on with the instrument. And then finally, operation started, and since then, JWST is really providing the best data we could ever wish for. I always bring this example. Many requirements. JWST is performing so well compared to our expectations. And the example I always bring is the stability with which we can point a target. It was supposed to have a stability within 10 milliseconds. The goal was 5, and actually we never measured something worse than 1.7. Okay, so it's really stable. So let's have a look at what JWST showed us. So with this GTO program, by the way, GTO is guaranteed time observation. Basically, when you build an instrument, you get repaid by time to use that instrument, okay? So a bunch of groups, especially led by University of Arizona, built NIRCam, and therefore they had a bunch of hours on cycle 1 to use NIRCam to do whatever they wanted. Oh, sorry, wait. So we looked at these 5 disks. Maybe you recognize some of them. I showed them before, but you see again, spirals, right? So we think the spirals are created by planets. Then we have the 70. We know there are planets there. TW Hydra is the closest protoplanetary disk to Earth. So of course, it's an interesting target for us. And then HL Tau is HL Tau. It's a beautiful disk. In my opinion, there was no reason to observe it, but anyway. So let's see why, in my opinion, there was no reason to observe it, because it's a beautiful target, but it's still very young and embedded in the cloud from which it's forming. And so when we look at it with JWST, here it's the data, raw data, as they come down from the telescope. You see that at short wavelength, 2 micron, we have all this scatter light from the envelope and the streamers, and it's really cool, but there is no way you can find planet in such a noisy image. But we did remove the PSF, and we try to understand if we see some variations, for example, in the streamer compared to what was done with HST in the past or other instruments. And we actually don't. It seems quite stable. Here you see a comparison with some ALMA data tracing shocks. And you see that we are tracing very well one side of the disk. Of course, the back side of the disk is covered in our infrared observations. We cannot see it. But we are really tracing basically the same structures. Most interesting to me, and this is the project I led for this program, is SAO 206462. Now, this is the disk. It has these beautiful spirals. And since the beginning, we looked at the spirals and we said, oh, there must be a planet for sure, 100%. So we looked at it, 4 different filters. You see here the residuals. Probably they don't mean a lot to you. The crucial point is there was no planet where we predicted it. But we found a companion candidate farther away in the system. Now, it's still a candidate. Basically, every JWST image we take, it's a deep field, okay? So we are still not sure if it's really a companion or maybe it's just a super high redshift galaxy, redshift 5, 6, or something similar. And we can only reobserve the target a few years later. And then depending if we see some movement or not, we can assess whether it's a background object or it's a real companion. But if it's a real companion, it would make sense because we now know that these spirals move with slightly different velocities compared to each other. And so this, and one of them is really consistent with a Keplerian object being roughly at that separation. So maybe it is a real companion. Yeah, sure.
So one thing is that you said that you look at this and you say that there should be a planet, but I look at it and I say, okay, it's maybe gravitationally unstable and you have spiral arms, but it doesn't need to have a planet.
Mm-hmm.
And then also if I'm naively looking at your, at your images, and I understand your argument that it tells you that the planet should be there, but naively, if I look to the left, I also have this bright point.
I was coming there. Good. So gravitational instability, the disk is not that heavy. We know this. And so if we trust our estimates based on the data from ALMA and so on, it cannot be gravitational instability. Regarding the noise, I always get this question. It's an awesome question. So we have this diagonal noise feature that we really gave our best to remove. And it's due to the spider and to the bright star and to the fact that JWST was performing so much better that we have 20% higher throughput than expected. This created this diagonal noise feature in the image. So when I mask this region, you see this is the only remaining source that is really convincing. And there is one more point. You see this negative, positive, negative pattern. This is what we expect for a true source. If you don't have this negative, positive, negative pattern, it's not a real JWST point source. This is due to the fact that our observing strategy implies that if there is a candidate or a companion, you would see it with this pattern. Okay, I will skip this and I will move directly here. So what can we learn about this system? So this is our typical sensitivity plots. Basically, we assess the sensitivity as a function of separation. And you can read it as this way. Whatever is above this curve could be detected by JWST. So we are learning something. Whatever is below this curve, we have no clue. It's too faint, it's too close in, we don't know. You see that our companion candidate is slightly below. This is because it was not within the 5 sigma threshold, but still we are convinced it's real. What is interesting is that all predictions from all the simulations based on this disk predicted the planet to be in this area here and predicted it to be at least 5 Jupiter masses in order to be able to create the spirals. And now this is the level of the 5 Jupiter masses candidate, right? We are definitely sensitive to this type of planets. So the fact that we don't see them leads us to believe that we are probably missing something. Either our simulations are not correct, either our understanding of the disk is not correct. Maybe planets are way colder at the beginning than we thought. I don't know. Or maybe there is one problem that so far we were not able to consider, which is extinction. So these planets form in protoplanetary disk made of gas and dust. So we know there must be some extinction in some form, right? Their emission must be attenuated. And this brings me to the second project I wanted to discuss with you today. Yes.
Can you just see that the opacity of the planet is just very different from what you expect, and that's why somehow
Yeah, this is the other option we are considering is if the planet is actually very large and very opaque, it would also be super cold, right? The same amount of energy that is emitted by a Jupiter of 1000 Kelvin could be emitted by a sphere of 60 Jupiter radii at 150 Kelvin. This is why we are trying to push in the mid-infrared with MIRI. But yeah. Yeah.
Do you see this candidate just in one band, or do you also have like sigma in one band?
No, we see it only in one band. And actually, the fact that we don't see it at 2 micron, where we have other data, give us this color constraint. This is why we can say that it's likely not a background object, but there is still a 3 to 4% probability it is. It's very, very red. And this is why I was saying that if it's a galaxy, it must be a high redshift galaxy. Okay, so we started thinking about extinction. This is something that in our observational papers comes out quite frequently now, but so far we have no measurement. This plot shows the extinction curve from ISM that most of us know very well. Now we tried to see what type of extinction we could expect in protoplanetary disks, and this is what we obtain. So it's a very different shape, and the reason is that in protoplanetary disk we have dust growth. So the properties of the grains are completely different than in ISM. Especially we don't have so many very small sub-micron sized grains. And so how can we try to probe this? Well, we found the idea. We think we found the ideal target. So this is AS209. On the right-hand side, you see the pebble disk. So here we are tracing the dust in millimeter. While on the left-hand side, you see the gas in seal. And there is a gap that I highlighted here with the 2 ellipses. But most importantly, we have a background source within the gap. And we think if we can manage to characterize the background source, we can then, if we know the intrinsic emission from the background source, and we can measure its actual flux, the difference is just due to the extinction in the protoplanetary disk. And so this would finally give us a number in terms of extinction to try to understand if we don't detect planets because they're not there or because their emission is lost within the protoplanetary disk. We are also trying to do the same with another target, very famous, HD163. Here you see the target is basically along the Milky Way midplane. And so you see that we have all the white dots that you see here are basically a background star, okay? And you see that there is an area in the center where we don't have any. And this is clearly due to the fact that we have the disk, and the disk is absorbing and scattering all the light from these sources. And then we have an area where we have some, and still it's part of the disk. So now we are starting to have a monitoring program to try to go back to this source every now and then. We have data from 2018. We are hoping to get data in 2025. And this is already a motion of 30 AU. So if we wait 7 more years, we have then 60 AU time span, and we can start mapping extinction protoplanetary disks. And actually, the whole thing began with extinction, but it's more interesting than that, because we can not only measure the extinction, we can also measure the dust column density in disks. And this is the first time such a measurement exists for small dust, micron-sized dust. And this is really interesting, not only for extinction, but also, when we try to play around with simulations, we always have to assume the amount of dust that we have. Actually, this could provide the first constraint and the first map of the amount of dust in protoplanetary disks. So we obtain a bunch of data. I'm not going to describe everything. Just beware, it's sphere, it's NIRCam. These 2 I'm still working on. Here, for sure, we have a detection. Here, I'm not sure, but it's a more noisy image. I have to work on it. All these data were taken a month and a half ago, or even less, so it's really fresh. But the preliminary results indicate that for sure there is extinction. Okay, and this is already something to learn. So this plot shows, let's start with the data. Yellow sphere, and NIRCam is shown in white. The orange line shows the fit if we don't assume any extinction. Okay, it's just a stellar spectrum. And you see that the fit doesn't match the data really well. Especially at 3 micron, we are completely off. And actually, even the NIRCam 2-micron filters, I'm showing the error bars there. It's just this JWST is super stable and precise. The error bar is between 1% and 3%. It's shown. And it's completely off. You see it here, for example. And the reduced chi-square indeed is around 8. But now we can include extinction. And if we include 6.2 magnitudes of extinction, we start ending up with something more similar to the blue line. And here you see that the reduced chi-square is much better, and the fit provides a much better, or the model provides a much better explanation to the data. Now, the question is, where is this extinction coming from, right? We know that the extinction from us to the star is like 0.1, so it's probably not that. But we don't know what is the extinction between the background source and the protoplanetary disk itself. So we're still working on that and try to play around with some galactic models now to try to have a prior knowledge of where it's likely this background source is in our galaxy. Yeah.
So, we didn't have to have the measurement in the studying lower part of the spectrum.
Yes.
Gives that extends the possible left.
Okay, you are asking a painful question. I made a mistake. We were supposed to have 3 more filters, 0.7, 0.9, and 1.1. And I chose a subarray. It's called sub 160, and I chose sub 160p. And apparently there's a huge difference between the two, and I didn't know it. So we lost those data. We are now trying to get HST to look at it. Yeah, absolutely. Absolutely. Because actually the next step is to move away from ISM extinction and try to play around with dust models, right? And when I do it, you see that the constraint in the near infrared is really good. And then in the optical, it's just going everywhere. It could be anything. So we need those data. Yes. Thanks for reminding me of my mistake. Finally, one interesting point that I wanted to add at the end is that we can look at this data set from 2005 that we used to assess that it's a background object. I didn't mention this, but there was a 2005 detection, actually. And you see that it's up there. It's a factor of 8 far away from the current brightness that we measure. So I still have to go back and I want to reduce this data myself instead of just trusting the results. But if this is real, it means that right now we are, or the projection of the background source is on a highly extincted area or a very dusty region, while 17 years ago, it was 50-something AU away, and it was actually in a region where the dust column density was much lower. So I think this is really cool. This is something to keep in mind. This is our motivation to keep going back to this source every year so that we can sample and map the extinction or in the dust column density every 3 AU. Okay, and now I want to move away a bit from protoplanetary disks and zoom into circumplanetary disks. So when planets form, we think that in the process, because of angular momentum conservation, similar to what happens in stars, also in planets, we have a circumplanetary disk that forms, from which the planets accrete material. And to discuss this, I want to introduce you to GQ Loop, which was originally the first, what was considered the first planet imaged around a solar-type star. It turns out it's a brown dwarf, but still, it's very, very cool. It was discovered in 2005. And since then, we managed to collect the full spectrum of the companion. And if you fit the near infrared spectrum, you obtain the dotted line. The dotted line is the best fit, and it doesn't match the 4.8 micron data point. It's completely off. On top of it, we know it's accreting. We see accretion lines. And so there was this idea that it's probably a circumplanetary disk around this brown dwarf. I keep calling it circumplanetary disk because to me, the important point is that it interacts with the circumstellar disk. Okay, it's not just about the mass of the companion. It's a disk of a companion that is forming in the disk and it's interacting with the circumstellar disk. Now, we were super lucky. JWST observed this source to look at the water in the inner disk of the primary. The PI of the program didn't even know there was a companion there. So I asked him if I could have a look at the data. He sent me everything. And together with colleagues at TTH, we managed to remove the PSF of the star and reveal the companion. Okay. Keep in mind, the MRS is this instrument that gives you the full spectrum. So you have a little image, and for each pixel, you get the full spectrum from 4.9 to 20 micron. Okay. And it was not meant to do this. There was no paper in, for every instrument, you always have paper presenting some simulations and predicting what the instrument will be able to do. This was never done. But actually, because of the stability of JWST, we can really try to do it. And of course, luckily, GQLoop-B was quite a bright source. So let's have a look at the spectrum. These are the near-infrared data I introduced you before. We have the 2 data points over there, and this is the atmospheric model. And this is the excess that was measured before and I mentioned before. And now we can overplot the MRS data that we obtained with JWST. And it's clearly a circumplanetary disk. There is no way this could be due to the atmosphere. What convinced me a lot about the spectral extraction is that we picked up, this is water in the atmosphere of the planet. And now you can just include an offset from the CPD, right? But we picked up the same feature over there. So this was really a convincing point. We don't see any silicate feature. It's expected to be between 9 and 10.5, 11 micron, right? So the fact that we don't see a silicate feature probably means that the disk is in a relatively evolved stage. The dust is large enough, more than 20 micron, and therefore it doesn't emit any silicate feature, and/or it's already settled in the disk midplane, and therefore it's not really accessible by our observations. We tried to fit this spectrum with some very simple model so far. So here on the top is showing again the difference between our actual data and the models for the atmosphere for GQLoop-B. Clearly no match. The second row shows we assume that the disk is the emission of the disk is best described by a simple black body. In this scenario, basically, we have a rim that is heated by the companion, by B, right? And from the temperature, we can estimate the distance of the inner rim of the disk, and so the cavity in a circumplanetary disk. And if this is the case, we measure 40 Jupiter radii. Just to give you an idea, all the Galilean moons fit within 28 Jupiter radii. So in there, we could fit all Galilean moons that we observe in Jupiter. And finally, the last model is a thin disk. So basically, we assume that the disk is very thin, irradiated by the brown dwarf. And in this case, we measure a cavity of only 8 Jupiter radii. And this would be consistent with dust sublimation and magnetospheric accretion. So basically, we don't know which one of the two is the correct one. We need more data. I have a successful program accepted, will be observed next year. So we will get the 3 to 5 micron data, because you see there is a difference here that we can try to observe to understand which of the two models is correct. And we will also get MIRI 12, 15, 18, and 20 micron data. So then we can try to expand the spectrum on the right as well. And finally, we also have data to detect the continuum from ALMA to understand how much dust pebbles we have in the disk. And this brings me really more or less to the conclusion. So JWST provides unprecedented sensitivity to detect forming planets. Overall, the observatory performs better than promised. We are now the limitation, and our data reduction is now the limitation. We see it. We know how to improve things. It's just taking time, of course. But expect in the next year to have even deeper limits, even deeper observations, and for sure, more planets detected. We have a few protoplanet candidates, and we are waiting for reobservations in order to confirm if they are really companions. But it seems that we are missing something somehow. For the first time, we are probing the properties of the small dust in disks. And I think this is really going to be a useful program for many, many fields in planet formation and disk physics. Finally, GQLoop is just paving the path to study circumplanetary disks. I think this is the new frontier for JWST. We observed another few circumplanetary disks, and they're just amazing. Okay, we see molecules, we see winds, it's really, really cool. And I think JWST is really, GQLoop is just paving the way there. It's the next year will be beautiful. And finally, October 16 is approaching fast. This is the deadline for proposals for cycle 4. If you have an idea, if you don't know if it's feasible or not, just ask. I would be happy to help and advise. I'm also helping out in proposal about X-ray binaries or high redshift quasars. So don't be shy if you have an idea and you want to discuss. I'll be happy to do that. Thank you.
You show the spectrum, right?
Yeah.
You also see some structure.
No. It's completely unresolved. And there is no way to resolve it with JWST. No.
Even if the spectrum will be brighter because it's a ground. So
yeah. No. It's 140 something parsecs away. It's far. I think at some point I ran some quick numbers. I think even Metis will not be able to resolve it. Yeah.
Yes, I was nice talk. I was wondering if you use different instruments to get one spectrum, you have to worry somehow that maybe they're not consistent with each other. So if you use HST data and JWST and whatever another instrument.
Yes, absolutely. You should. I think that so JWST and HST being based in space, the calibration is really good and stable. Okay, we have more problems from the ground. And indeed, for all these fits, what we do, oh, sorry, too much. What we do, so we have a bunch of HST data in the near infrared, and whenever we can, we fix the yellow spectra to those values. And for those that don't have any corresponding HST data, we just have them free to float around a bit in the y-axis. Because the absolute calibration is difficult from the ground. We have the atmosphere, we have the thermal emission from the telescope itself, from our atmosphere. So it's a bit more messy. But JWST and HST usually they are super stable. And indeed, when we observed other targets, the match in the spectrum between NIRSPEC, MIRI is amazing. It's really there. So we are quite confident that the calibration is stable. And yeah.
So on the disk with the marginal planet candidates, so JWST, so you said the gravitational stability is unlikely because the disk is too low in mass. You know, what's the constraint in the mass? How large is the error environment? From what to what?
I can go back to you on this. I don't remember the values. No, I don't remember the values. I would just shoot random numbers here.
Because what I often see is that people take the critical mass for instability. Not, it's usually that mass is the mass for fragmentation, right? You could have this that isn't stable and lower mass doesn't fragment, but is still able to form storm spiral. Often that's kind of a misleading point.
I see. I have to go back and see what we do. Yes. Let's talk about this.
Then it gives you really a lower bound for the mass, while the actual disk mass could be higher.
Exactly.
Yeah.
Which is sometimes often being ignored. So
Yeah. And of course, there was a dust to gas ratio that was assumed. Yes. Of course.
Then I also have a question about this object. So you said it's a ground rock, right? And we expect to have a disk. And then you had the comparison with Jupiter, but actually, you know, with the Galilean satellites, right, and where the disk is.
Yeah.
But actually, it's a much, much larger object.
Yes.
So my question is, can it be that it's not a disk, but it's something that, you know, within the disk around it, you know, something happened to the solids or there are some gravitational interactions, and it's actually not a disk, circumplanetary disks? Would there be any other way to
But what would it be then?
I don't know, like, you know, you could have solids, and then because of this object, you can have collisions, and then you break some dust, and then.
So you mean like a orbiting cloud?
Something that is not necessarily a disk.
So, well,
I mean, what are the constraints that is actually a disk in terms of geometry?
well, we see accretion. No, in terms of geometry, there is nothing. We see accretion, right? We see H alpha, Paschen beta, and another one that I don't remember. And we see, so if you take the black body fit, the size is 27 Jupiter radii. So it's you know, because I got the question in the past, could it be a big moon or a binary brown dwarf system? And the answer is no, because the radius is too large. Right.
But can it be many small objects, for example?
I guess this is possible. I guess, yeah, it could be a big cloud. Yes, I think this could be possible. I didn't publish this. I'm still working on it because I'm not 100% convinced, but I think I see molecules. So if we see molecules, again, it doesn't mean it is a disk. No, it doesn't mean anything. No.
Okay.
So no, the answer is no. We cannot be 100% sure it's a disk at the moment. Yeah. Yeah.
I mean, is there a circumstance disk?
Yes.
Yes. What's the mass? Is it a massive disk or is it?
Again, if you believe the mass conversion, it's quite massive. I don't remember the number, but it's more massive than TW Hydra and many other disks.
So there's still presumably a lot of gas.
Yes, yes, yes. We see a lot of gas. Yes, yes. And actually, the data we are getting with ALMA is deep continuum, and then we will get these high-resolution CO observations to really see the companion and the disk material interacting with each other, like I was showing at the very beginning here. We will do this with 100 meters per second resolution on this companion orbit interacting with this disk. So we will really be able, in principle, to see the spirals and see this interaction live.
Because that could help us understand that whether conditions are closer for a certain.
Exactly, exactly. Yeah. Yeah.
So, is there one more quick question, I guess? So when it comes to a comparison to other X-band detection methods, what's the distance to the solar system that you can observe planets?
Okay, so
just the neighborhood, or can you actually?
So for this type of science, protoplanetary disks, because all except for two, all protoplanetary disks are 100 parsecs away, we are able to probe, let's say, with JWST, I would say from 15 to 20 AU onwards. If you move to H alpha, because H alpha is the optical, you can push into, let's say, 5 AU or so. If you look to close targets, right, there was this paper on Epseri, one of the fifth, sixth closest targets we have. They detected the planet at, I mean, they could be able to detect the planet at 3, 4, 5 AU easily with MIRI, and yeah, with NIR come even closer in probably. Yeah. But never like a transiting planet. No, no, no.
Okay, let's thank Gabriele again.
Yeah.